All right. Looks like we're ready. Nobody's here yet, but I guess y'all watch it later. We're going to do a couple of things today, or at least I plan on doing a couple of things today. We've got some Solidworks Topology Optimization. This is a really cool thing you can do in Solidworks where you can build kind of a base, kind of blocky model, define a couple of things, and then Solidworks, will go through and it will come in and optimize your geometry based on some design constraints that you set up. So we'll do that. We can't actually run the simulation during this time just because it takes a significant amount of time. The one I did ended up taking about an hour to run. I suppose that is dependent on your computer you're using, but they're going to take a while to run. So we can't actually run the thing. We can set it up, and then I can show you what the result looks like. And then assuming that doesn't take very long to do that process, we'll look at some TPU, so some flexible material. So let's go over to SolidWorks. Let's go over here. Get that on the screen. There we go. This is what we ended up with. This is kind of the final result. Now it looks all kind of jaggedy and everything, but you can export a smooth version, and it looks like this. So a little bit better. So this is some kind of little generic shelf bracket made out of Delrin. I didn't have a plastic material that kind of mimics a 3D printed material. So I just used Delrin, which is it's kind of a tougher plastic, but it is plastic. And I was one of the constraints I was using needed a material that had a yield strength put into the processor, and a lot of the plastics in SolidWorks that are built into it don't have yield strengths because plastics, they're not metals, so they operate a little bit differently. But Delrin did have a yield strength listed, so yeah, that worked. Now, you normally don't actually print this part. You could, but if you, even on the smooth version, you can kind of see it's not that attractive looking. I did set this one up to where it has symmetry, so that the one side, left side, is the same as the right side, just a mirror image. But it's still not, I don't know, it doesn't look that great. Normally what you do is you use this thing as a kind of template to design your part, so that you kind of, make a neat, clean part that you would actually print. So the idea here is that let's just start out. We'll just build this. Let's just do that. File new. Let's do a new part. Again, we won't be able to actually simulate this one because it took for that one, it took about an hour to simulate it. So that's going to be too long. But let's just go in here and make us something similar. Now, whenever I'm streaming in SolidWorks, I get these weird redraw like this kind of thing. So I haven't figured out what makes that not happen. So we'll have to deal with it. It clears up, and then it, whenever it's redrawing stuff, there's some, I don't know, it's a driver issue or something. I don't know. It still works. It just looks weird. Let's see. Let's make this it's like a shelf bracket that you're going to put a piece of wood on. And let's say that's maybe a 12-inch shelf. So let's make this a 8-inch top up here, and let's make this some reasonable number. 7 would be about, let's do 5. Let's see what 5 looks like. May not be quite long enough. Let's do 6. I'm just guessing on all these things. It doesn't particularly matter. Let's make it way thicker than that, though. Let's make it 1 inch thick. Okay. So what we're doing now is we are going in and blocking in kind of the volume that we want our part to exist in. Later, not today, but probably tomorrow, we'll go to Fusion 360, which is also a modeling package similar to SolidWorks. Got some differences, but it's similar. And it takes a different approach to the same type of thing. So SolidWorks calls this Topology Optimization. Fusion 360 takes the approach of generative, what is it called? Generative topology, generative design. can't think of the exact phrase for it, but it ends up with a similar thing. But it just takes a different approach. We'll see how they're different once we look at both of them. Let's put a little top on here. So let's do extrude on that guy. I want to look at it. And again, it's going to probably do the... No, it actually didn't do a lot of crazies there. Oh, I didn't want another one. I wanted to... Oh, no, not what I wanted. I want to do a rectangle on here. There we go. Now, let's make that 8.25 so it hangs over the right side by 1/4 of an inch, and then let's make all of these 1/4 of an inch. None of this, these dimensions are just whatever you would want them to be. We're not actually designing anything. We're just kind of putting some dimensions out there so that they kind of look like what we want. That's way too thick. All right, so now we have a little part on top. We need some holes in here so that we can actually screw it to the wall. So let's do extruded cut on this surface, and let's put, oh, not that big, something like that. And let's make these, let's just do 1/4 inch diameter for these holes. And let's make them, well, that's fine. But let's make that for construction. I wanted it to be longer, but it didn't end up that way. So that's our little construction line that we can line these guys up. Except I don't want it that way. Oh, let's just do it this way. I'm not even sure that that ended up straight. Let's just do it this way. This is not the best way, but this will work for what we're doing. It'd be better to create a line on the midpoint and put the whole centers on that line versus actually defining them to be 1/2 inch, because what if I wanted to change the width here? But I don't want to change the width, so it'll be fine. Let's make that one 2 inches, and then let's make not sure what it did there. I think I didn't click the right spot. Let's make that one 4. That'll be fine. All right, that looks great for what we want it to do. So first step is to create kind of the space you want your object that you want optimized to exist in. So the way this one works, Solidworks Topology Optimization, is that it doesn't really go outside of the, like, it doesn't create new volume anywhere. This is kind of the outer boundary, and it will eat away at all the stuff it doesn't think it needs. So there's our little bracket. Let's just save that. Sometimes there are issues, you know, with particularly I've got streaming going, there's a web browser going, SolidWorks is going, so it could be a lot. Let's put it in its own little folder here, and we'll call it bracket. Actually, it didn't go in the folder, did it? There, bracket. Oh, I already have one, bracket 2. Okay. All right. Now, this is the part where there are different versions of SolidWorks. So, if you don't have the same version, you may not be able to do the topology optimization. I am not sure. I know SolidWorks has a kind of what do they call it? I don't remember what they even call it, but a free, not free, it's cheaper version. Let's see if we can find that information. SolidWorks, we don't want to remove the 3D Experience Marketplace. Let's download. Let's see. Let's go to SolidWorks and see. I know they have a demo, but they also have a new product that is affordable. Like it's, I don't know, $70 a year or something like that. But I don't know where to find that. I don't want to request a demo. All right, so there is an academic license. This is the one I think I was thinking of. Maybe student edition. SolidWorks for 3D Experience Works. That's something different. Let's see. This one, 3D Experience SolidWorks for makers. Let's see what that one. It may not have simulation in it though. So it's buy now. Let's see. I just want you to know, like if you don't have a version of SolidWorks, if this is even possible, it may not be. Let's see. It says, but this is 3D Experience SolidWorks, so I don't know what that means. But $10 a month or $100 a year is reasonable for what SolidWorks offers you. So that part is good. I just don't know if it has all of the stuff that would let you do the topology optimization. I don't want to watch a video about it though. I just wanted to list out the parts. It doesn't mention it, so I'm going to think that unless you have a full version of SolidWorks with the simulation, and it's not just the simulation, it's the so in your add-ins, let's see if it'll let me show you. So SolidWorks Simulation, SolidWorks Premium is actually not going to do this. You need SolidWorks Simulation Premium to be able to do anything other than just a static simulation. So if you want to do some kind of transient thing, or I think even the thermal stuff maybe, and the topology optimization, then you'll need the SolidWorks Simulation Premium option. So if you're at school, then you probably have this, but it's not turned on. And even if you click on simulation, if you don't explicitly go in and say, no, I want to use SolidWorks Simulation Premium, like check right here. Normally just SolidWorks Premium is selected and it'll let you do a simulation, but it is just the simulation for static loads. So you have to go in and manually check that you want the Simulation Premium option. Then when you go to run a simulation, you'll have a lot more options. We'll see in a second. So we have saved our little bracket. I've got Simulation tab open here, and we're going to do New Study. And see how all of these little buttons are lit up? Oh, I never noticed there was a submodeling one. It's not available, but that's interesting. If you don't click on SolidWorks Premium Simulation, you'll only get this first one as an option, which will not do the topology optimization. We want to do topology study right here. So if you're noticing these buttons and they're there, but they're all grayed out, kind of like this submodeling one, then you need to go activate the premium version of it. So if you're using SolidWorks from school, then that you do have that. It just may not be turned on when you load up SolidWorks, because it does take a lot of overhead. So a lot of times you turn a lot of these things off just to get SolidWorks to run faster, load faster, and then you only turn on the ones you need. So we have done that already. We're going to do topology study. All right, and yes, we could name it something if we wanted to. All right, so what we need to do here is basically go down this list of options. There is a wizard, kind of the same options are across the top. I don't know, you can use either one. I usually go down this list, but the same things are kind of across the top in order of what you need to do. So first of all, we don't have a material defined, so it does need to know what kind of material you're going to use. Now this is something that I'm sure SolidWorks does, and I just am not quite sure how it does it. But I like the way Fusion 360 does this a little bit better, because they realize that if you're doing, or in their case, generative design, you're probably doing that because you want to print this part. It doesn't have to be printed, but they have options where you can limit the algorithm, the iterations, the finite element solver to certain manufacturing processes. So like machining or additive printing or molding, things like that. Here you don't really seem to have those options. Maybe they're built in somewhere. There are manufacturing controls, but it's not quite the same. You could create something here that kind of does limit it to something like a CNC mill operation versus generative, any kind of geometry. But anyway, we got to assign a material. So we're going to right click. In my favorite materials, none of these, unless I wanted to make it out of metal, which you could make it out of metal. Obviously, you're probably not going to print this in metal unless you have access to a much different printer than the one sitting over here. But if you want to do a plastic one, this always takes a while to load up, so I'm going to go ahead and click on it. You either need to, hey, it didn't take long at all. You either need to go in and define a material, or find one of the few plastics that they have built in. So here's some plastics. And what you want is one piece of this process, which I suppose you could do this process differently, but I want to apply a factor of safety. In order for the simulator solver to actually use the factor of safety, your material needs to have a yield strength. Most of these have no yield strength listed, right? So you could edit one to create a yield strength, but I did notice that Delrin, it has a yield strength listed. Nylon, I think, where's it at? I saw some nylon in here. There they are. They have a yield strength listed. So there are some of these materials with a yield strength that's listed in there. The polycarbonate does not have one. Acrylic actually does have one. No, most of them don't have one. Actually, that one, oh, that's Delrin. That's what I did use. So you either need to create a material, don't use a factor of safety as your design goal, or use one of these materials that does have a yield strength listed. So you got to apply some material. I can't do anything without a material. So I've got a Delrin bracket now. I'm not going to use any connections, but I am going to fix it. So for a simulation to work, you can't just have this part floating in space. It's sort of like you've created a free body diagram, and now you've got to go in and put some constraints somewhere. You know, what's holding it in place. So I'm going to fix geometry for this one. What I'm going to do is I'm just going to fix just the circles around the holes. I don't want to fix the entire cylinder, because that will preserve the whole cylinder, and I don't necessarily want that, because I just cut these all the way through the part here, and I don't really, that would maybe be cool, but then I'd need some weird fasteners, really long ones or whatever, or countersink the holes or whatever. So I'm just going to just select the whole circles there. So we'll check that. Now what will we do? Let's go to add a load. So let's just add a force on top here, on this top surface, right there. And this is just a little, what to do, make it 8-inch bracket, shelf bracket. So, you know, there'd be multiple of these, at least 2 of these holding up a shelf. And you're not going to put something super heavy on this. So let's just put that this guy is going to have to support at most, I don't know, 50 pounds. That's probably way more than this would need. And if you overload it too much, so you do have to be realistic. If I put like 500 pounds on here, then it's not going to remove much of the material at all. It probably needs most of the material. So be realistic on the loads that you need to apply here. So, you know, what do you want to rate your shelf bracket for? I don't know what shelf brackets are rated for. They're probably different things for different shelf brackets. So maybe let's just do 25. We're not actually going to run the simulation, so it doesn't really matter. And we'll check that. So now it's sort of like I've been setting up just a finite element simulation, because that's what's going to happen. Is SolidWorks is going to run this as a finite element simulation, but it's going to run it over and over again and remove material each time based on where it doesn't see a lot of stress, and run the simulation again and remove some more material and run it again until you have kind of reached whatever design goals you wanted. So oh, I forgot something. Let's go back to features and let's build a symmetry plane. So let's create a plane here that's based on that surface and that surface. That'll put a plane of symmetry right through the center of it, so that I can ensure that it's a mirror image. One side is a mirror image of the other side. So there we go. Now we'll go back to our simulation. And in our goals and constraints, let's pick one of these. The default thing is best stiffness to weight ratio. So we could do that. And that's probably a faster simulation. Why don't we do the default one? I did not do the default one on the last one. What I did was I minimized mass, and inside that minimize mass option, I also told it that minimize mass while maintaining a factor of safety of 1.5. Here, best stiffness to weight ratio is the default. Let's just leave it on that this time. And reduce mass percentage by 30% is its goal. I've made this pretty blocky, so let's say that the goal, and now it doesn't weigh anything, it's only going to be 0.5 kilogram, but let's say the goal is to reduce this by 50% if it can. And now if I want this factor of safety down here at the bottom, that's where you need a yield strength. I don't know that I actually need a yield strength just to do this part. Manufacturing control. So we can say that, hey, some of this stuff is important, don't go changing it. So we're going to add a preserved region. So let's say that we don't want the top to be changed, because that's got to sit flat. We don't want it eaten away in all holes in the top thing. In fact, why don't we preserve all of these and the bottom side, so that we kind of keep that top shelf part that's going to interface with our piece of wood that goes on top of the bracket. Let's keep all of that. I need to keep this back surface, but I want to do it separately. So add a preserved region here and this one. And I also want to preserve a certain depth of it. I don't want to just have this surface. I want it to be a certain depth. And let's say that we want that 1/4 of an inch. We've done 1/4 of an inch for everything else, so let's do 1/4 of an inch here also. So that'll mean that this surface has to stay 1/4 of an inch thick, and then it can start removing material. Okay, we'll click that. See, we want a symmetry plane. That's why we made that plane 1. And you can do other symmetries. You can do quarter symmetry or eighth symmetry if you had some radial type of thing. We're going to do half symmetry. See if there's any others here. A thickness control. This one would actually be useful because we want to print this. And if you'll notice, let's go to our previous one. Yeah, this one. We did end up, this is the smooth version, we did end up with some relatively thin little pieces here that would be difficult to print. Although apparently, technically, they would be strong enough, but this is also simulating a bulk material that's been machined away, not something that's printed. Printed materials typically are not isomorphic like a bulk material would be. So it's probably better that we go in and say that, hey, you might be able to make parts thinner than this, but let's go to topology study. But we want everything to be at least, and then we can specify some thickness here. They've got them as 0.2. They got this weird number. Let's make it 1/4 of an inch. We could also do maximum as well. And what else is in here? Demold. So demold direction is if you're going to mold this, You can also use this if you want to do like machining from one direction. It would also not create parts with overhangs that can't be demolded or machined from one direction. So we don't need that limit because we are going to go in and assume that this thing is going to be 3D printed. So we've got our load on the top here. We've got a little bit of geometry that's going to hold it in place. We've got some preserved regions. We've got a plane of symmetry. We've got a minimum thickness. We don't have a maximum thickness. And you would just right click. I'll let this run, but I'm pretty sure it's not going to finish. Although I did do the goals differently than I did last time, so maybe, I don't know, but we'll see what it looks like. So this one, SolidWorks, as far as I know, doesn't give you a preview of what it's doing geometry-wise. It does give you some convergence curves, so you can kind of see that it's progressing towards a solution or not. But Fusion 360 actually kind of gives you an update on, hey, here's where I'm at now. But the difference is SolidWorks is going to run this simulation locally. So if you've got SolidWorks installed on your computer is going to run the simulation, which is good in the sense that it's running locally for you. That's bad in the sense that it's only using your computer's processing power. Fusion 360 runs in the cloud, which means you have a whole lot more processing power. It'll actually run multiple simulations at the same time. The downside of that is that it may not always be free. So far, and I have a .edu account, so that's probably why it is this way. But it is free to run the simulation or it was. I haven't run it this year, but the last time I ran one of these, which was in, I don't know, January sometime, it was still free then, but on Fusion 360. But they are using Amazon Web Services or whatever to run these simulations kind of in the cloud. Fusion 360 is. So it does give you a lot more processing power, but it's not always going to be free. So just be aware of that. I'm just going to click Mesh and Run here. Obviously, SolidWorks itself is not free, so you have to have a license to SolidWorks somehow. And I guess someday I need to download, or maybe somebody can tell me that has the maker version of SolidWorks if it has topology optimization built in. I'm sure I can Google search that. So you get this little pop-up. It's going to run, I don't know, 50 to 100 iterations on this thing. And one iteration is basically it's solving the finite element solution that we set up here with the boundary conditions and the forces and the material properties. It's solving that, looking for low stress areas of your model and removing some of those low stress areas, solving that solution, and just iterating on that. Looks like we do have a convergence data that we can look at now. So it's not going to show much yet, but we've got two targets here. One is we wanted it to get down to 0.3 kilograms. Currently it's at that. And we also wanted to figure out what the best stiffness to weight ratio. So you have these two graphs. You can kind of see that red line there is, hopefully after we'll let this run a little bit while we're talking about TPU, and it'll have made some progress on this. You can kind of see it's starting to approach some number over here. And the mass target, you can kind of see there's our target, that blue line, and it's, looks like it's, going to head up here somewhere. So we'll let it run a couple of, actually it's going relatively fast. It's already done 6 of them. When you do the factor of safety, it does slow it down quite a bit. So this one, without using the factor of safety, just using the default mass constraint of best stiffness to weight ratio, it does run faster. So maybe this will be done by the time that we are finished talking about TPU, because it's actually going really fast right now, 10% done. All right, we'll let it sit there for a little bit. Actually, let's look at one of these. Yeah, you can kind of see starting to, drop back down a little bit. And this one's also, it's going to, sometimes they bounce around a number, and other times, like when there's a target, it's going to, that's not the one. This one. Oh. I might have, there's, it's suddenly slowing down on me. There, it'll try to create a kind of an asymptotic approach to that target line. Although now it's found some solution here that kind of made the mass worse, but it's probably trying to optimize the stiffness, you know. So we'll let it go do that for a while. All right, so let's close that guy down and let's look over here. So, oh, one thing, since this is out here, this is a quick thing. So remember, well, at one point, oh, I think maybe when I cut this here, I said that if you don't have something like this is the little TPU cutter that comes with, I think it came with the Capricorn brand tubing for a Bowden tube. If you don't use one of these, you'll end up with something like this. Let's see if we can get a close view of that. So this end is cut with these little guys. So they will go in and close up the Bowden tube, which is obviously going to be bad if you're trying to push filament through there. So if you want to change Bowden tube, these things are usually given as part of a package for getting a new Bowden tube. If you don't have one of these, make sure you do have some sort of really sharp, thin razor blade that you can use. These do a pretty good job of keeping the cut square and round. So you get not only is it square on the end here, there's a little channel down there that kind of holds the Bowden tube square, but you don't crush the end like you do with your little snipper things. So if you ever need to, these are not expensive, and like I said, just buy whenever you want to deal with changing off your Bowden tube. Even if you don't want to change out the Bowden tube, remember it does go down in the hot end, and over time you might need to snip the end of that off because it's gotten worn from being so close to the hot part of the hot end. All right, so that's these little things. You can print these also. You just get a razor blade, and there are some prints available that kind of create something like that, that keeps the Bowden tube square and chops it off pretty cleanly. Just don't use these because they're going to create problems by squishing your tube. All right, so that was just kind of an aside. Let me make sure that I can still, all right, we're at 25% on the other thing. All right, so I wanted to do some TPU printing. So TPU is a rubber thermoplastic. So it's like I think the U might be urethane. I'd have to look that up. But I got, let's show you this box. So got this little heater box here. Oops. That was some glue. I just got the Sunlu one. There's a couple of different brands. They all look basically the same. There are two different styles to this, though. There's this style that actually is a heater. Not a very powerful heater. It's like, 55 degrees Celsius. I think it can go up to 60, so it's not really heating a lot. The idea is that it heats enough to remove any moisture that might be in your filament. TPU is one of the filaments that's generally going to absorb moisture and not print very well when it is that way. So there are these kind that actually have an active heater in them, and you can kind of set a time and temperature within, I think this one does only go to 60 degrees, which is probably not quite as high as you would like to really evaporate moisture, but in 5 hours or something, it should have evaporated out the moisture that is on the surface of your roll here. So if you're printing something like this, is ABS in there, and I've also got the little TPU packet on the back side over there. So some materials, nylon in particular, ABS, TPU. Those are the ones that I'm coming to mind. PLA does do this, but it's not nearly as bad. You'll read all kinds of things online. You know, somebody will post that I don't ever dry any of my filament, and it's never a problem. And you read further and like, oh, they're in Arizona, so it's not very humid. But here it is pretty humid. You know, our average humidity year-round is 70%. So it does get where these hygroscopic materials, like particularly nylon and TPU and ABS a little bit, it's also this way, they will get moisture absorbed into the filament. And if you don't bake that moisture out or pull it out with desiccant, then your prints may still work, but they're not going to work very well. You know, you're going to have what looks like retraction issues. Your surface finish is not going to be very clean. The material itself might be very brittle. You might have noticed, even on PLA, like if you had a roll sitting around for a while, the first little rolls wraps from the outside that you pull off might just snap. If it does that, then it's brittle and it is not going to print very well. And that brittleness is usually from moisture absorption. So this kind of little box is just a little heater chamber thing. You can actually print from this. There's another kind of this that looks basically the same, but it doesn't have a heater in it. It's just a closed container for desiccant. So you put desiccant in there, and it pulls the moisture out that way. So I've got my little roll of sample TPU. So TPU is a material that is flexible, so rubbery. Oh, it's off the screen. So rubbery. This one's new. This is this stuff. It came in a little maker box thing. So this is transparent green from Hello 3D. Normal printing temperatures. Says the bed doesn't even have to be heated, although I will heat it. Speed is slower. Now it does show a speed at 50 millimeters per second. That's a little bit fast for most TPU, but this one does feel a little more rigid. It doesn't feel too flexible, but you know, it is definitely flexible. Some of these come way more flexible. Some of them come pretty rigid. This one's kind of in the middle. So maybe that's why I can print it a little bit faster, but it does say that you might have to go all the way down to 20. Doesn't say if you want cooling or not. Normally it doesn't make much difference on most of this. For best results, a direct drive extruder is recommended. Fortunately, we did our little upgrade here that put the Bondtech direct drive DDX system on this printer, so that's good. You can print TPU, maybe not the very softest TPU, but you can print flexibles on your Ender 3 with the Bowden tube. You are going to have to basically turn off retraction. There's not going to be much ability to do retraction, so you might as well just turn that off. It's going to make a big mess otherwise. And you will probably have to print slower. So, but you can get it done. Even on this one, I'm probably not going to want to do much retraction just because I can, because the unconstrained path is really small on this direct drive setup, but it's retracting a flexible is usually not very good. It doesn't say anything on this one. Why I want to print this one is that this one's transparent. I haven't seen a transparent one before, transparent TPU, so I want to print it and see what it's like. Now, a couple of things. Let's turn our printer on. A couple of things, though. The surface. So I've got this textured PEI build plate. Generally, you don't want to print PEI or TPU onto PEI. So I've got a couple of boxes over here. Let's see. I've got this box. It's actually kind of in the way here, but this is where I keep all the various build plates that I have, or at least some of the ones that I have. It's the box that the Creality glass plate comes in. It comes with, some little foam to keep everything kind of not broken. So it's a good box to store build plates in for this size machine. So here's the Creality glass plate. Now it does have a textured surface on here that I don't know exactly what this material is, but the other side is just plain glass. So we could use that. We could just print straight on glass. That's usually a good TPU thing. TPU on PEI is going to bond pretty strongly, so it can pull the the PEI off of the build plate. I've got some other options. Let's see. This one would not be good. This is a PEI non-textured from the Prusa printer. This would be good. Maybe you don't want to go get one of these. This one is literally a Walmart picture frame. It's got a bunch of hot glue on it that I cut down to fit on an Ender 3 bed. So you can get you a couple of dollar glass cutter and a few dollar picture frame and cut your own sheet of glass. Now that does, it's a little bit sharp on the edges, so you got to be careful. The Creality one is nice and rounded and sanded. You can sand glass to make it not as sharp. I've got a couple other PEI. Yeah, I've got the original bed that came, the Ender 3 bed. You can print on either side of it. I'm going to print on this Creality glass bed since got it out here. Now, it is not magnetic, so it's not going to just sit there. And I just now thought about that, and I'm not sure where I put my little bed clips. I might have to... Oh, is this them? No, it's not them. I might have to do a little quick search to find them. We can do another thing if we have to, but let me see if I can find a bed clip or two, or maybe take some from a printer in here. Oh, our simulation ran. It didn't do quite what I wanted. All right, so these are kind of bulky, but we'll use these to hold our bed down. These are way too big, but I don't want to spend the time to go find the right ones. You just have to be careful that you put them in a place where your print head is not going to run into. I'm going to put them at pretty close to the front and back, so that this one may hit the purge line. I may have to move it off. Anyway, our simulation, let's look at this. It did run, but let's look at it. It didn't come out the way I wanted. So, you can kind of see where it's beginning to modify this. But with our constraints, it said that most of this, the yellow color here, is, we can see on the side over here, that's must keep material. And this constraint was a, what did we set it up as? A mass constraint. We reduced the mass by 50%. So let's change that and say that, no, we want to reduce the mass by a lot. We want to reduce the mass by 85%. So that it'll really go in there and try to optimize this thing. That is usually, they kind of look cool because you end up with these kind of unique geometries. But usually what you're trying to do is do a light weighting process so that you have the lightest weight piece that's going to actually do whatever performance it needs to do. That one did not take too long to run. So let's see if it'll run this one in a reasonable amount of time. Let's see if it'll tell me. It may not tell me while the simulation is running. Yeah, I can't look and see, but it'll tell you how long it took to run. But it looks like it only took 15 minutes or so to run, the previous one. Now, trying to reduce the mass by 85% might make it run a little bit longer. I don't know if that'll finish. Let's go back to our TPU. All right. It can also create a situation where it can't be done, like you're asking it too much, and so it can fail. All right, so TPU on glass, usually you want a release agent. This is why I didn't want to put, I don't want to put this on my PEI bed. I don't mind putting it on the glass. It is water-based, PVA glue, and it's easy to wash off of glass. It's just on the textured PEI sheet, I don't know, it just is harder to get out of the texture. So I'd rather print on a glass sheet. A couple of things to think about, though, when we go to print is I've added a glass, a pretty heavy, at least a lot heavier than our little thin sheet of spring steel with some PEI coated on it. This is going to potentially, if I had optimized my motion system to print as fast as I possibly could, move, accelerate as fast as I could, now that I've got this much heavier sheet on there, I may not be able to do the same accelerations that I was doing before. Now, I have not done any of that with this slicer. I haven't, or this firmware, or any of it. I've kind of mostly default stuff. But if you had, you might have to go in and drop your accelerations in particular down, at least the accelerations on the y-axis, because you've got significantly more mass now. That if you accelerate that, or you try to accelerate that mass too fast, then it could skip some steps. So I haven't really done any of that, so I don't need to worry about it, but it is a thing to think about. We're already 12% on our simulation, so it might actually make it. Let's load up Cura so that we can print something. I'm going to go ahead and preheat. There we go, and we'll preheat the bed to 50. I mainly want to preheat the bed so that the glue stick will spread out nicer. So I'm on the back side, just the clear glass side. I've never actually cleaned this. I probably should wipe it down at least. Let's see. So I've just got my isopropyl alcohol that I'll kind of clean a little bit just to say that I've done it. It just came out of the box. I've never used this sheet before, so it's brand new. All right, so that's preheating. Cura is open. Apparently there is a Cura 5.1 beta available. I don't want to do that right now. Let's just drop a, I don't know what kind of part. I want something quick so that we can actually see it. Let's do a cylinder. There we go. We're going to change this to, I don't think that was it telling it had warmed up. Let's see, this was called, what was this called? Hello 3D. That's probably not one of a bigger brand. Yeah, it's not one of these. So we're going to use generic TPU. So 95A, now the bed is also heated up. 95A, that talks about how rubbery it is. So we'll go with that one. We will discard these changes because I don't want to figure out what they all meant. This printer, this printer has, so remember, the flow rate was really messed up, right? It looks like I never changed it to be a 0.6 nozzle. I changed the line width, but I don't think I ever told it I had a 0.6 nozzle in there, which I believe I do. So let's go and change that. That was why a couple of days back we were getting some really weird flow rates that said that we needed to reduce flow by like 60% or something, because I'd never changed here that we were actually using a 0.6 nozzle. 0.4 layers. 0.4, that's probably, that's a bit much. We have the 0.6 millimeter nozzle in there right now. So 0.4 is, let's just do 0.3. We'll do 2 walls, 2 top and bottom layers. So the rubberiness of the TPU part is controlled by the number of walls and the infill. So you can make it pretty stiff by increasing either the walls or the infill, or you can make it much more flexible. The benefit is that you don't fracture it when you flex it. So kind of how soft it is depends on how dense you make the part. Let's make it more soft. Let's go down to 15% with 2 walls. It's saying the printing temperature is at 228. That's from setting it to this generic TPU. I'm gonna drop it down to 220 because that's the upper range on our bag. You know, I'm just looking at our bag here. Print speed, it's at 50. We do have direct drive. It does say that we might be able to go up to 50. I'm actually going to drop it down though to 40. I've always had better luck with TPU printing it slower, but I haven't printed it on this direct drive thing. We'll have cooling on, no support. We'll have a skirt, and we'll slice it. All right, so it says it's going to take 14 minutes. That should be right at the end of class. So let's see how this works. What did this call it? I don't even know. Oh, Bontech, no, Untitled. Okay, so Untitled is it's the only Untitled on there. All right. So we're over here at the printer now. Oh, you know what? I should have previewed this to, okay, it looks pretty normal. Print, Untitled. Now, another thing that if you don't have a bed sensor on here is this is a lot thicker than the sheet that was on there before. So if you're not using a bed sensor, then you're going to need to adjust your in-stop for Z, because otherwise you're going to crash into the bed. That is, even on these small printers, that, oh, you know what? Hold up. Stop. Stop. I never loaded the filament. So we need to do that. All right. So let's, now again, this little sample is not on a spool of any kind, so it might give us some problems, but it's a short print, so hopefully it'll be all right. And it's not going to roll very well because it's kind of grabby. So we're changing out, just so you can see, changing out this. So remember, it's usually best to push down and then pull out so that you kind of remelt that bulb on the end of it. Loading this stuff is a little bit tricky because, well, loading it through all these things. Although, I'm going to try to give it a point on the end here to try and get it to feed in there. It's just I think it did it. All right, so let's see if we can purge some of that out of there. Let's. All right. I do have some of it purging out. Movement, extrude. I think it's grabbing it, but do a smaller amount. Not certain it's actually grabbing it very well. Might need that part. Yeah, it didn't actually grab it. Loading is actually easier in the in a Bowden tube printer than it is in this kind of printer. But we'll get it. I think. If not, I'll get it loaded later if we run out of time and show you the part next time. Oh. It all fell down. I think the pointed end is actually working against me here. Let's cut it off straight. I have to go there. Well, let's check on our Solidworks. Solidworks is actually 80% done. We might have to go back to that while I work on getting this fed into here. All right, let's see if we've got something stuck in there. This is some PLA that I'm just trying to make sure there's nothing, like the path is open, which that's one downside to this particular path, is that you can't get anywhere in there like to actually guide the filament, and so it has to find its way in there, which it's not doing right now. Oh, all right, so I did get it to go this way. All right, so let's see if we can get the flexible to do the same thing. It's just so much more difficult because it wants to curl up just that little bit that it won't hit the spot just right. Maybe. can actually feel as it is hitting the different levels in there that it needs to go through. %99 on Solidworks. Well, all right. So let's look at our Solidworks. It came out way different this time. We'll come back to that. I might have to do it off screen just because it takes so long. So look what we got this time. Really different. Really different. So it thinks that in order to reduce the weight by 85%, that this is what we need to do. Now, again, it looks, you know, it's all jaggedy. These jagged edges are a function of the mesh density that you were using. I did not change the mesh, so we use whatever the default mesh, which is probably just kind of average mesh size. You can go in and change that, make it more coarse or more fine. Over here, if you right click, you can export a smooth mesh so that it is kind of smoother. I will make it a new part. Okay, so file, open. And we put it, where did we put that? Oh, was it in just new folder 2? I think that one is it. So here's our smooth version. So I don't know that I actually like the way it created the first one. The first one also had the constraint of a factor of safety of 1.5 on it. This one does not have a factor of safety built into it. It's just reduced the weight by 85% and figure out the best stiffness to weight ratio. But this one ran in 15 minutes, where the one with the factor of safety ran in an hour. So you can kind of see how this will work. I think you get better results when you use the factor of safety. It just takes a lot longer. Let's look at it again. You know, you get something like this that, okay, that looks more like something I would expect. I could take this and use it as a template to draw up the actual bracket. You know, in this particular case, this is probably something, well, I could have figured out that on my own, sort of. But it is a way, we're using a very simple geometry, simple loading configuration. But so topology optimization in SolidWorks, this is how you do it. There are other options you can add in there. I would recommend doing the factor of safety option, which does mean your material has to have a yield strength, and it means it's going to take a lot longer. So 15 minutes just to get something, but the something you get is, you know, I don't know, that kind of, you can kind of see some of the tree branching type stuff. This one does have the minimum feature thickness of 1/4 of an inch, although that part right there doesn't look like it's 1/4 of an inch, so I don't know if it completely adhered to that or not. Maybe it doesn't count that as a feature. But it is an interesting thing. Normally you don't use the actual results, you use the results to create the design later, based on what kind of the solution would do. And then you would still run a finite element analysis with your actual loads again. So like whatever you create, you'd run an analysis on that shape just to see, make sure that it's not something that the solver thought was okay, but you don't think is okay. So I think we're probably, I'm going to close these down, and I'll spend some time, I don't want to save any of this, I'll spend some time trying to get our TPU loaded, and look what it did. This is what the unconstrained rolls, look at this. They always do this. So typically you don't want that. That's what we have now though. Our bigger problem is we got to get our filament loaded. So I'll come back. Eventually I'll get it to go directly in there the way I want it to. And I'll print the part. We'll look at that the first thing tomorrow. and we'll look at Fusion 360's generative design, at least that's the plan, and how it does this same process. I may have to pre-do it also. I'll try and build a similar bracket. I don't know if I'll remember all the numbers that I built or not, but a similar bracket and see what Fusion 360 comes up with. All right, I will see y'all tomorrow.